Heisenberg's uncertainty principle states that the more you know about how fast an object is going, the less you know about where it is, and vice versa. How can this be? Find out on today's episode of Quantum, Basically. Now, I'm going to be heavily referencing last week's video on Schrödinger's cat and indeterminacy, so if you don't know about that or you didn't see that video, the link is in the description, go check it out. Now, Heisenberg's uncertainty principle is actually an equation, but I'm not here to show you a bunch of math. I'm just here to tell you about the cool stuff. I'll save the math for my students. Now, I stated at the beginning that the idea of the uncertainty principle is that the more you know about how fast something is going, the less you know about where it is. Now, if you know your quantum, first, I don't know why you're watching this. This is the basics. You know this stuff. Maybe it's just refreshing. Good. Hi. Second, you know that it really shouldn't be speed. It should be momentum. Momentum is really simple to explain, but it takes a while to develop an intuition for what it is. For the purposes of this video, I'm just going to say speed. So here's what Heisenberg is saying. If you measure the speed of a particle really precisely, like really precisely, you know it, you know exactly how fast it's going. In the act of measuring the speed that precisely, you lost the particle. You have no idea where it is. And it's the same thing for position. If you measure exactly where a particle is, you have no idea how fast it's going, because in the act of measuring its position that precisely, you lost track of how fast it was going completely. You changed it. Now, this is not a statement about how good humans are at measuring things. It really sounds like we just need to find a better way of measuring our particles, because it's like, man, you measured how fast it's going and you lost it? Come on. It's like, do better. No, that's not what this is. It's indeterminacy. To start with, the particle didn't have a really precise place or a really precise speed. It had kind of a mishmash of probabilities of different places and different speeds. Whatever you can do to make the particle have a really precise speed makes it have an even less precise position. And if you measure the position really, really precisely, you make its speed indeterminate. It's not just that you don't know how fast it's going, it's that it doesn't have a precise speed anymore. It has that mishmash of probability of speeds. And I won't do it here, but using this equation, we can figure out exactly how imprecise the speed is going to be for a certain precision of position. And that sounds really crazy to say for like a larger object. It turns out that based on the nature of this equation, it doesn't work out quite the same with larger objects. It's technically true for larger objects, but you're never really going to notice its effects. It's really when you get down to particles that you start to notice this. An interesting example is that if you know, for instance, that an electron is on the left half of its atom, you don't know how fast it's going to the point where you don't know whether it's fallen into the nucleus or like flown off and isn't even part of the atom anymore. We actually use Heisenberg's uncertainty principle to figure out how big the atom is. It's just based on how much we can even know about how fast the electron is going, and not how much we as humans can know, but how much information even exists. This really isn't a statement of human limitation. It's a statement about information not existing. Don't be too concerned. It's not like everything is indeterminate, right? It's not like we don't know whether it's really an electron or some sort of wave or something like that. Next week. Subscribe to this channel if you want to see next week's video on wave-particle duality. Yes, there will be other videos between now and then.